Okay, so first of all, let's have a look at factorial, let's say 5, and gamma of 6 will be gamma of 6 will be factorial 5. So these are the same. Now have a look at this, factorial 1 point, actually let's stick to gamma. Gamma 1.4. There we go. What about gamma 1.5? Well, it's that. What about gamma of 1.5? There it is. So that's equal to factorial 2.5, I guess. Is that, and then if you square it, you get pi. So gamma of 0.5 is pi, or the square root of pi. It's nice, isn't it? And if this was a theoretical course, I would spend the next 14 weeks talking about different gamma of 1/2 root pi, which is quite an astonishing thing. I could prove that if I wanted, but it would take me weeks and weeks and weeks, and it would be completely boring and pointless in this course. Who'd have thought that pi, which is defined in terms of geometry and circles, would crop up in a generalization of counting? This is quite an astonishing piece of mathematics. All right, so let's just define a function. Let's just define f becomes a function of p alpha beta, which returns gamma of alpha plus beta over gamma of alpha let me just type didn't like that, did it? Let's just try that again. Gamma of alpha plus beta over gamma of alpha times gamma of beta times p to the alpha minus 1 times 1 minus p. I know there's quite a lot to take in here, but all I've done is type this formula in our language. It's just that. There we go. Did that work? And now I can choose what happens with alpha and beta. So I'll show you what happens. Plot, no, actually, p becomes a sequence there's my p, it's just a sequence from 0 to 1. Plot p, comma, f of p, let's try 5 and 9. All right, so I've just chosen 5 and 9. That's alpha and that's beta. This is my function f, which I've defined just like this. And that's what it looks like, which we'll see in a minute forms a beautiful prior for using with Bayesian analysis. And we'll see what happens in a few minutes. But for the moment, just observe that it's defined nicely between 0 and 1. I won't do it, but I could demonstrate that the area is exactly equal to 1. And now I can start playing games with this 5 and 9. Let's have another try. Let's try 50 and 90 and see what happens. With 50 and 90, see they're in the same ratio here. I've just multiplied by 10. See, it's made a nice sharper picture. So this would correspond to a prior for P of somebody who's pretty sure that the probability is around about here. And they'd say, and you'd ask them, is it 0.2? And he'd say, no. That's way too small. Is it 0.6? And he'd say, no, it's way too high. So this is representing somebody who's quite confident about his value of P as a prior PDF, okay? If I go back to 5 and 9, this is somebody who's very much more uncertain. They don't really know where it comes. Yeah?
So I just clarify prior, just what you think it might be.
Yeah. Your prior is what you think it might be. Your prior is your expert judgment, your knowledge of similar things, past experience, and of course, I'm thinking my past experience is trying to get my 3 kids together in a photograph. My 3 things, my examples are from my world, but you must think in terms of your world there. Let's try some more ones now. Let's try 598. There we go. Perfectly good prior for somebody who thinks the probability of success is around about 10%, but pretty sure it's not as high as that, and it's absolutely not as high as these guys here. Let's try it the other way. Let's try 98, 5. Oops, should be a comma. And that's gone over to the other side. So we can fool around with this all day. Rather than defining that function, remember I defined this function f here, which was this here. I just did that to show you that you could do it if you wanted to. What you need is d beta.
You still have to define your p, alpha, and beta, though.
Yes, you do. Now, everyone in the known universe calls it alpha and beta, except here, where it's shape 1 and shape 2. So, yeah. So that's alpha, and that's why I don't know, but that's just the way they've done it. And who am I to argue? I'm not covering the non-centrality parameter. Yeah, it's a bit messy. I might cover the log, and the lower tail just works the same as it works for p chi-squared and for p norm. All right, so there it is. So I can do this a lot better. I can go plot p d beta of p, let's say 2 and 3. There you go. And again, so you should be picking up an idea that as these numbers get large, that corresponds to a nice tight prior. There's lots of information there. And if these numbers are small, 2 and 3 are quite small numbers, we've got this broad distribution. Okay? Here's somebody who hasn't got a clue what p is. But if you had to say, you'd say, well, it's probably smaller rather than larger. Let's try 1 and 1. What's going on here? 1 and 1, let's go back to the PDF. Forget that constant there. We've got p to the alpha minus 1. I'll write that symbol there. It's proportional to, there's a constant of proportionality there, which doesn't depend upon p. 1 minus p, beta minus 1. But in that case, alpha equals beta equals 1. And so we've got p to the 0, 1 minus p to the 0, which is constant, of course. But it doesn't change, indeed. It doesn't change because it's to the power 0. So you may as well forget p, because it's to the power 0. So here's why this is controversial. There are 2 views of this. The first one is this is a prior for somebody who has got absolutely no idea what the probability is. That person says, I've got no more reason to believe it's down here at 0.1 than here or here. I simply don't know. This is one way of looking at it. This is a representation, a mathematical representation of perfect ignorance. Okay? Because it's horizontal. This person's got no more reason to believe it's there as there. Look at some of the other ones. Here's somebody who says, oh, I'm a bit more certain it's round here, but I'll probably, yeah, but he's got some beliefs about it. Let's go back to the uniform prior. Uniform prior, which is this. Oops. Absolutely no information. That's one viewpoint. There's another viewpoint, which is taken by the majority of statisticians, which says this. This person, on the contrary, who presents this as a prior, is presenting a huge amount of information. He is saying, I am absolutely certain that I've got no more belief in there, as there, as there, as there. This person is making an assertion of uniform prior probabilities. I'm sorry.
They're claiming that they don't make any assumption whatsoever.
Yes. That's one view. And the other one is that this is an assumption. The way to frame the argument is I'm not prepared to equate your statement of ignorance with about P with my statement of knowledge about this uniform prior. Two.
Talking to somebody who knows nothing about mathematics, it sounds like a cop-out.
Sorry, it's not like a cop-out, or it is?
It sounds like a cop-out. If one person is claiming their ignorance, yeah, I have no idea. And the other person just sounds like they're trying to cover their ignorance.
Sure, I think that's a very good characterization.
By stating it that.
It all boils down to what you mean by ignorance. If I say I don't know what P is, what does that mean? Does that mean that you do know it's a uniform prior, or does that mean I don't know? And I don't have good answers to this because it's an ongoing academic debate. I could give you my beliefs. In fact, I will give you my beliefs later, but I need to establish this first. Let's give him a tiny bit of information. (1.1) and 1. You see, 1 and 1 was perfectly uniform prior. 1.1 and 1.1. See how it's almost uniform, but it kind of falls off towards the edge. And you can pick that up from the formula. If you put 1.1 in there, you've got p to the power 0.1 here. 1 minus p to the 0.1 there. So it falls off. What this person is saying is that, but probably, and okay? Indeed. We can do this. What do you think is going to happen? Huh? You think so? Pretty much. What does this say? What a person who gives you this as a prior, what are they saying? He doesn't know. It's either 0 or 1. He says, well, I don't know whether it's going to be almost exactly 0 or 0.01 or something, or 0.999. One of the two, but it's over there at the outside. It's either impossible or going to happen with certainty. I don't know which. I need more data before I can pin it down. But you can see how we've pushed that out there. Sorry, was there a question?
So anything under point, under 1 means that it actually is going to be the extremes that are the problem.
That's correct. 1's the cutoff because 1's the perfect uniform. And so, which way around? Bigger than 1 means you've got the spike, and smaller than 1 means you've got the U-shaped curve, yes. And of course, you can carry on playing games like this all the time. I can give it 1 bigger and 1 smaller. Let's have a look at that. Yeah? So there's somebody who thinks, well, it could well be certain, but I'll probably buy it being a 90% probability, and yeah, do you see how it's kind of a spike, but it doesn't come down again because of that negative. This is a very flexible distribution. Flexible. It's useful. And I'm not quite sure what the right word is. Well, I may as well just say there's no real alternative to the beta. There is a book in the library called Beyond the Beta Distribution that gives you mathematical alternatives, and without exception, they are completely worthless rubbish. The beta distribution is a wonderful, wonderful, wonderful distribution. Because it's got this great flexibility, and as we'll see in a few minutes, it's got this great power. Let's get the Wikipedia page up, and I'll just quickly go through the Wikipedia page. I'm not sure why that turned itself off. Go to Google, type beta distribution in, and if you think you know better than Google, all right, but I don't. So I just click on the first one, which is the Wikipedia page, which is an excellent source of information. And I've added bits and pieces to it. Again, I want to emphasize again, don't beat yourself up for not understanding the beta understanding the whole page, because I don't understand all the page. Not all of it anyway. It's Control plus to make it bigger, isn't it? There you go. So you can see that on the page it's traced out some of the distributions like this, and we can see the bimodal distribution here and this green one here, different combinations of alpha and beta. What I'm interested in is this information box down here. Support between 0 and 1 is a member of the set between 0 and 1. The PDF is as I've given you. It's in a slightly different format. That B is just what I've defined. CDF I'm not covering. It's quite complicated, that. Mean. We all understand what the mean is. Alpha over alpha plus beta. In particular, if alpha equals beta, you can see from the definition, if alpha equals beta, then it's symmetric between P and 1 minus P. So if alpha equals beta, you've got to have a mean of a half. All right? And that checks out here. See how I'm applying very simple... I'm substituting into this formula simple values for alpha and beta, like alpha equals beta, just to check if it works. But what we can do is, let's try. Let's verify numerically, verify that if x is distributed as b, no, beta of alpha and beta. Let me just say this formula again. The random variable x is distributed as a beta random variable with parameters alpha and beta. Then the expectation of x, which is the mean of x, equals alpha over alpha plus beta. I want to verify that numerically. I'm going to try okay, 4.1 and 3.8. So let's just have a look at that. (4.1) 3.8. You'll see it's that connector, isn't it? Which one was it? Oh. Whoa, well done. I'll talk for another 2 minutes and then we'll have a break. See how R for random, it's the same pattern as R norm, P norm, Q norm, D norm. We've got a D beta as well, which I could have used instead of defining it myself. There's the numbers. I can make a histogram of them. There's my histogram. Why does it suck? It sucks because I've only got a sample of size 10. Right, there you go. Now, I predict that the mean is going to be 4.1. That's what I predict the mean is. Should be close, yeah? Give me a break. So it looks like that formula holds true. I want to encourage you to do that as a habit. When you see a formula, some of these things are pretty bad to do. We could do it if we wanted. But look at this one. The mean value, the expectation of x, the mean value, is a very simple formula, and I've just verified it. Numerical verification is very powerful it's a lot more convincing than I could prove it with mathematical formulas and integration and all this rubbish. But it's a lot better just to do it and just to ensure that you understand what's going on. Let's have a look at the variance. So here's the variance, and it's this complicated formula here. Let me write that out. Alpha beta over blah, blah, blah. All right, let's have a look at that. The variance is that. What was the, I can't remember the formula. Let's put that over there. Oh, there it is. Alpha beta over alpha plus beta. Oh, for goodness sake. Ugh. 4.1 and B is, what was it, 3.8?
Yes.
Just see what happened there. Here's a formula. I've got no reason to disbelieve it, but it's nice to check. Let's just whack it in, and you see all I did was write down A and B instead of alpha and beta, and I just A, B, alpha, beta over A plus B squared times A plus B plus 1. That's the numerical value, and here's my numerical estimate of it, which is pretty damn close. Sometimes above and sometimes below. All right, I'm going to stop there. We'll have a break for 10 minutes, and then I'll reconvene, and I'll show you how to make use of this distribution after the break. Thank you.